So now let's see an example of this. How would this actually happen in real life? Okay, so to do this, let's look at another example of a qubit. So it turns out that photons have this property called polarization, which carries a qubit of information. Okay, so here's a way to understand this. It's sort of a semi-classical kind of interpretation. So light is an electromagnetic radiation, so you think of it as being carried by an electromagnetic wave. So let's say that the light is moving in this direction. So it's going from here to here. That's how it's moving. And now the electrical field oscillates in the orthogonal direction, but now it can be oriented. So if it's going like this, then in this direction, then the electrical field oscillations can be oriented, let's say, either horizontally or vertically or at some diagonal angle. The state of the polarization of this photon, we'll think of a horizontal orientation of this electrical field oscillations as the polarization state of the electron where the state is 0. And if the oscillations are vertical, then the state is 1. But now what happens if it's diagonal, if it's at a 45-degree angle? Well, then the state of polarization, the state of this qubit, is 1 over square root 2 0 plus 1 over square root 2 1. Okay, so basically what you get is a qubit where this is horizontal polarization, or it's also usually written like this. This is vertical polarization, which we call 1, or it might be written like that. And then you could also have a polarization that makes any angle, and that's the state of the qubit, that this qubit, the polarization qubit that this single photon is carrying around. How do you measure this the polarization of a qubit? Well, you use a polarizing filter, a polarizing lens. Now, this is the same kind of polarizing lens you might have in your sunglasses. What it does is, the lens has a certain orientation. The filter has an orientation. So, for example, this filter might be vertically oriented, which means what it does is, if there's a photon coming through and it's vertically polarized, then it goes through. But if it's horizontally polarized, then it gets blocked. So it's performing a measurement. It's letting the photon through if it's vertically polarized, blocking it if it's horizontally polarized. But what if it's a superposition of vertical and horizontal? So let's say that it makes an angle of theta with vertical. So it's in the state cosine theta vertical plus sine theta horizontal polarization. So now what happens is exactly what you'd expect. So it gets transmitted with probability cosine squared theta. By the way, if it gets transmitted, what's the new state of the photon? Well, it doesn't matter that it was diagonally polarized when it came to the lens. If it's allowed through, then the new state is exactly this vertical polarization. And then it's blocked with probability sine squared theta. Now, of course, the other thing you can do is you can change the angle of this lens. You can change the orientation of this lens. So you can change it so that it's pointing at a diagonal angle. And then what happens to the rules of transmission? Exactly what we said. So for example, if you rotate this angle so that the lens is oriented at 45 degrees. So now suppose the lens was oriented like this. Now that corresponds to a measurement in this basis. So photons which are polarized diagonally like this are transmitted. Photons which are in this orientation get blocked. Okay, so let's see an example of this. So let's say that you take two such lenses, one of which, the one in the back, let's say, is oriented vertically. The one in front is oriented horizontally. And so now what's going to happen to light? Well, the light comes in. So by the way, I hope you understand that when you're looking through this lens, you're looking at a very large number of photons. And each one is transmitted or blocked depending upon its polarization. But the net effect is, you see the light being cut down by a certain amount. But now, for the quantum version of this experiment, we are imagining that we only had a single photon that was going through. Okay, so what happens to that single photon? So let's say that its original orientation was cosine theta up plus sine theta horizontal, vertical. So now what happens to it with respect to the back lens? Well, it's transmitted with probability cosine squared theta. But now if it is transmitted, the new state is definitely up. Now what happens when it encounters the front lens? Well, that lens is horizontally oriented. This photon is vertically oriented. So it's blocked with probability 1. Okay, so no light gets through. And that's why you get this dark spot here where you have the two lenses juxtaposed. Okay, so now let's change the scenario slightly. Let's take a third lens and we interpose it between the back and the front lens. So we put in a middle lens. And this middle lens is oriented at 45 degrees. So what happens now? Your first intuition would be, well, the light was blocked, you're putting something more in the middle. Surely that makes it even harder for the light to get through. And so if it was dark before, it should be doubly dark now. Well, let's go through the analysis. The photon was in this state. It encounters the back lens. What happens? It's transmitted with probability cosine squared theta. Its new state is vertical. Now, at this point, it encounters the middle lens. Okay, so let's see now what happens after this. So the photon is vertically polarized. The middle lens is oriented at 45 degrees. So it's transmitted with probability 1/2, and it's blocked with probability 1/2. But if it is transmitted, what's the new polarization? Well, the new polarization is 1 over square root 2 up plus 1 over square root 2 horizontal, right? It's a 45-degree orientation. Okay, now it encounters the front lens. But the front lens is horizontally oriented. So now this photon, which is polarized sort of diagonally at a 45-degree angle, it gets transmitted with probability, again, the square of this, which is 1/2. And the new polarization of the photon is horizontal. So the net effect of all this is that it's interposing this lens in the middle. What it does is it gives you a quarter chance of transmission after this, after whatever the transmission chance was on the first lens. And so you interpose the lens in the middle, and suddenly what you get is a faint amount of light coming through, or some chance of transmission.